some work which we are doing here in Kolkata, again as Dipankar said, with a group of students in our project here. And they have presented several posters. Many of you might have seen them, but I just summarize the contents of various posters, nothing else. So what we are interested here is in asking the question that all of us know that there exists entanglement even in single particles. For example, many speakers have said there exists single particle entangled states. Okay, for example, path spin entangled states, and experiments have been done. We have heard talks by Rao, Khaze-Rao, etc. Now the question that we raise is it possible to implement some very basic information processing tasks using such single particle entangled states? So here we go. First of all, again very briefly, regarding the status of these states. Now one knows that the framework of quantum mechanics allows for the existence of entanglement between various degrees of freedom. Okay, so there is nothing special about any particular. It has to be the spin or continuous variable entanglement, or only in one thing. So there exist hybrid entangled states, which there is nothing in the framework of quantum mechanics which says that such states do not exist. And indeed, there have been several proposals over the year. Actually, Zukowski in a paper in 2001 sums up the situation from the point of view of understanding these very clearly. And there have been many such states which have been implemented experimentally. For example, entanglement between spin and linear momentum, polarization and angular momentum, energy level in spin, etc., etc. Now, as far as the top few lines are concerned, one can think of spin of a single particle with a linear momentum of another particle. Okay, but also at the level of single particle itself, there could be entanglement. For example, entanglement between the possible paths and the spin values of a single particle. And indeed, such entanglement as a theoretical proposal have been presented several years ago. There was a early work by Ohm and Kerr on this in 2001, and indeed Hasegawa and Rao et al. Have implemented it in a paper in Nature in 2003, particularly using neutron states for path and spin variables. Now, the question, as far if one does dwell slightly into the deeper nature of quantum phenomena, if one believes in quantum field theory, then there is nothing to suggest that there is any difference between single particle excitations and two particle excitations. So all possible properties of single particle states should be similar in this sense to properties of two particle or more states. And indeed, even the concept of non-locality or violation of local realist inequalities have been proposed for single particle systems using, first by Hardy, then GHZ has worked, and recently, a few years ago, there was a proposal by Wedder. Although so far this has not been tested experimentally. So given this background, one would tend to ask, so if there exist such states, how about using them for information processing? Single particle, path spin entangled states, let's be very precise. So now, what are the difficulties? The major difficulty is normally when we are used to talking about information processing using anything, we speak of entanglement which is separated. For example, we have two qubits which are located at two different locations. So now, in this case, the picture is not that. We have an entangled qubit or two qubits located in the same particle. Okay, and this could be 3 or 4 qubits as well. If you find more variables for a single particle, there could be more entanglement that could be stored at the level of a single particle. Now, when one tries to do information processing, what are the disadvantages of such states compared to, say, standard 2-qubit entangled states for two separate particles? So these are the issues which we are trying to understand. So I will very briefly, I have no time to talk about any details, but what I intended to show you in this talk is that just first describe very briefly how one does indeed set up a path spin entangled state of a single particle. Then using it, again, let us try to see if it can be used as information processing resource. So the first step, it can be swap that path spin entanglement onto the standard spin entanglement of, say, two separated qubits, two particles. That is very easy to do, that we have done. Then a teleportation protocol which uses such a path spin entangled state as a resource. And finally, very briefly, our recent foray into key generation using such states. Okay, so first setting up a path spin entangled state of a single particle. So let us start with a single particle, okay, which I can label the path coordinate by psi 0, and then let's say it's in a spin up state. Okay, so here is the pictorial scheme very briefly. So one can think of a single spin up particle falling on a beam splitter. For example, let's take for simplicity a 50-50 beam splitter. So there could be two possible paths here, transmitted and reflected. Now, suppose in the transmitted path I introduce a spin flipper, which is a unitary operation, then what happens is the spin up turns to spin down. So now you see that for everyone knows that spin is a dichotomic variable, spin half. Now, path here is also can have two possible states, okay, this path and this, T and R, okay. So I can treat this also by pseudo Pauli spin matrices. So the emergent path spin entangled state one can write down is as follows: alpha, sorry for the qualities of transparency, so this is up spin, okay, tensor product, this path which I call 1 plus iota beta, this is the reflection coefficient of the beam splitter, reflected path downstream. Okay, so this looks exactly similar to a 2-qubit entangled state that all of us are familiar with. Okay, so what are the properties of such states? Now I can just change my notation. Instead of 1p, I can think of it as another dichotomic variable. Okay, so I will use the standard notation from now onwards. So this is the state that everybody has seen. So these are dichotomic path and spin variables. So essentially 2 qubits are carried by a single particle. Now this is intra-particle entanglement. To repeat once again, this is distinct from the entanglement of spins of 2 different particles, or even hybrid entanglement of, say, polarization of one photon and the spin of another spatially separated photon. And this state is a true example of a single particle hybrid entangled state that we will use. So now the first protocol that we want to swap the entanglement that is present in the state onto the standard within quotes that we are already familiar with, entanglement of 2 qubits, 2 particles which are spatially separated, 2 spin qubits. Okay, so what do we do? Again, initially the 2 qubits are disentangled initially, of course, because we want to make them entangled. They have to be started as disentangled, and they have no interaction among them. Okay, otherwise the whole purpose is defeated. Now the protocol proceeds as follows. Suppose Alice is a path spin entangled state which I label by 1, and a second particle 2 which is in a spin up state. So the second particle 2 is again a very standard example of what we deal with every day, but the particle 1 is a path spin entangled state. And Bob has particle 3, which say is also in a spin up state, again a standard single qubit, single particle state. Now what we want to do is to, through some local operations and classical communications, the state of 2, that is the path spin, the second particle spin up state, and 3 get entangled while the path spin entangled state 1 is destroyed. Again, exactly like a standard swapping protocol, except for the fact that we are trying to swap the entanglement of an initial single particle path spin entangled state. So the protocol is actually it's very easy to see. There is nothing, deep or mysterious about it. Again, one can perform this C0 operations, and one has to be sent to Bob after this. Okay, and Bob also combines, does some unitary operations, and finally there are 2 Stern-Galak apparatus. So this is essentially similar to a Mach-Zehnder setup. And the other point about it is I'm only talking in the context of, in this talk, spin-half particles, but exactly similar things could be done with, say, photons. We use polarization instead of spin, and paths are the same. So finally what do we get is that 2 that was with Charlie and 3 that was with Bob get entangled at the end of this protocol, and these 2 particles have never had any prior interactions. Okay. Okay, so let me not, I think I should better move on very quickly. No time for the details. So the final outcome is that this Psi2-3, which is shared by Charlie and Bob, look exactly similar to a standard 2-qubit entangled state. And this intraparticle entanglement that was present in particle 1 is swapped onto the spin-spin interparticle entanglement of 2 and 3. Now again, to make sure 2 and 3 never interact with each other, otherwise there is no point in this game. Okay, so now one can say that once you have transferred this entanglement onto 2 separate qubits, one could do information processing with it as one does normally. But there is also another question which may be of slightly academic interest, is that if you are not wanting to do swapping, just use that single particle path spin entangled state as a resource for information transfer. Is it possible to do that or not? So because I have to end in another 4 minutes, okay, so let me not, but the method is similar again, the protocol, let me not just spend too much time on it. So again, it happens similarly, and we compute the the fidelity, etc. of this, and finally this state is used as a resource for information transfer of a 2-qubit state. So very briefly in the last 2 or 3 minutes, let us dwell on the key distribution protocol, some work which we have just begun. A paper is on the archive last week. Okay, so what we want to do is we want to set up a key distribution protocol using such a single particle path spin entangled state. And what are the steps of this protocol? Of course, there is the main important first phase, key distribution itself, and we are using single particles, okay, but these are entangled particles. So this phase proceeds exactly like the BB84 protocol. Now, that is not enough. We have to also ensure that security of this protocol is there. And here we have an advantage because these particles are entangled. Now we could try to use the EC3091 scheme and test for the violations of Bell's inequality to check the security. Now in this case there is no, this entanglement resides at one location, okay, inside a particle. So in this case violation of Bell's inequality would correspond to violation of non-contextuality. And again, after Eckert's talk in the morning, such violation may have nothing to do with quantum theory. It could be also by PR boxes, okay. But I won't have anything to say on it. And what is the other important feature of this protocol? That the data which is used in key generation is complementary to the set of data that is used for security checks. So we do not need to throw away any data. So if any one of you is interested in the mathematics, there is a poster put up there. Please have a look. And I will have to end. I cannot go through it. So much time. So finally, this is the summary and conclusions. So we are trying to devise protocols for information processing through single particle hydrogen entangled states. And we have devised a couple of protocols, that is swapping and teleportation. And finally, a key generation protocol, security check that we have started. And here is the perspective. I actually said, I need not repeat it again. And the next, one of the goals of this program is to actually see how noise affects such states. Could it be that the entanglement is located at a single position? Is it more robust against noise effects? Okay, so this, some theoretical work has to be done and we have begun doing it. Thank you.
We have 4 to 5 minutes for questions.
You are speculating that because it is entanglement is only in the single particle, it could be more robust. But on the other hand, if you are entanglement, you will be considering superposition of 2 paths. That probably will be more prone.
Yeah, no, I'm not speculating. I'm saying that it has to be worked out and understood. For example, interesting things like entanglement sudden death, which occur if 2 different Hilbert spaces are involved. Or sorry, 2 different environments are involved. How does it happen in such a system? So I'm not speculating, I'm trying to see that whether we can do that.
Are there any other questions? Sir,
can you go back to your beams in the matrix?
Which one?
I think it was in the second or third slide. Yeah. Now, so what is the role of that I in that matrix?
So,
the I mean,
no, I, it's reflection. Reflection, I consider.
And alpha and beta are real or complex?
Alpha and beta in this case are real.
Real.
Real, this case are real. So I comes because of the reflection.